Alright, good afternoon. This is the last lecture on support vector machine, fifth lecture. So we'll discuss all the problems which you will practice about 4 and 3, 7 and 2, 9, approximately 9-10 problems we'll do, so that you can get hang of it more. So what did we have done? The very first lecture when we formulated the optimization problem, we said it's going to be minimal, maximize 2 over norm of W or minimize half of W transpose W subject to Yi times W transpose Xi plus B greater than equal to 1. So that was the primal problem. Then how to solve the primal problem? We said we're going to make cases out of it. So we solved that problem. Then we said we don't work with the primal problem, we work with something called as a dual problem. The dual problem is where you work with the Lagrangian of the function. So you maximize the Lagrangian, and the advantage of that is that the input space, the feature space, gets collected as an inner product which we got to change. Then last class what we did is we changed this, that we allowed some outliers to come here and there, and we called it as the soft margin. So if we have to recall where the soft margin had stopped, we had the soft margin was, so the soft margin problem which we derived was this. Everybody comfortable with it? No, you don't go to work with. So the difference between the hard margin and the soft margin is only a C comes as a lower bound, where C is the error which you are allowing for every point to go inside the margins. So that is the zeta times C, the constant which is going there. This constant is adding up in the objective function. Okay, so that is what we had done. And we had derived this also. I'm assuming that you are comfortable with it. Now we are going to talk about something called as the kernel trick. This we briefly talked about last time, but we're going to go over it again. So far we have considered large margin classifiers with the decision boundary, how to generalize it to more nonlinear. So you say you transform the X to a higher dimensional space to make your life easier. So you say X is the input space, phi is the feature space. So if you look at this figure which we went over last time, if this was your data, you can see it's very difficult to build a linear classifier, although you can build a linear classifier like this and have some outliers with a soft margin. You can still do that, but it could be that many points are going inside the boundary. So the better way here is to transform the input space to a feature space where it may become linearly separable. So there is a theorem in machine learning which says that if you take the input space to a higher dimensional value, the data may become linearly separable. So it's not guaranteed, but there is some intuition behind it which says it may. And how much dimensions you want to increase, which space you want to take, it's all very subjective. You have to figure that out. The example which we are going to see today is it's a 2-dimensional space, and then we change it into a 6-dimensional space, and there it may become linearly separable. So that is what we're going to see. So another example is this one is definitely no soft margin would have worked even if you would try to do a linear classifier with a linear hyperplane with a soft margin, it would have not worked. But when you did the transformation, it became separable linearly. Okay, so what is the kernel trick? The kernel trick, the name kernel, again, like I said last time, comes from something which is very core of a problem or something. Kernel typically is, we say, almond kernel, something inside the outer shell. So here the kernel is, this inner product. So everybody agrees this is the dual problem with soft margin C. So instead of doing this, we'll write it as an inner product of 2 other functions. The idea being that Xi and Xj, for example, are 2-dimensional, 3-dimensional, 10-dimensional. Phi Xi and Phi Xj, which will be a variant of the corresponding Xi and Xj, will be much higher dimension. Okay. So we call this as the input space and we call this as the feature space. So we're going to replace this with k of xi xj. So that is what is written here. So the original function was this, you can see this is that, and the changed function is just you replace it with the kernel function and increase the problem dimension. Yeah. Input space is, we are saying that input is directly coming from the data points, right? Feature space is where, this is also features because these are input features. It's just a nomenclature that we are trying to say, we're going to increase this dimension. For example, let's say you've got this breast cancer data points, you've got 10 data points related to benign or malignants, x1, x2, x3, x4. And we're going to use that as the inner product here. The dimension of xi is, let's say, it will be clear in a minute. Just with this example, it will be clear what is feature space. So now what we do, we have to figure out what this kernel function is or what you're doing with the feature space. So this is an example which we're going to work out. So the kernel trick says, so earlier, let's say, we had the inner product xi transpose xj, and then it is two dimensions, let's say. Two dimensions means that xi is xi1 and xi2. You can write it different ways, right? In the regression case, we had written this as like this. The superscript was going for the point and subscript was going for the dimension. This is how we had written in the regression case, but here we are just putting the dimension along with the data point itself. So xi is this and yi is I'm not saying yi, it's another point yj which we are saying, so it's xj. J is the point itself. So this is xj1, xj2. I and j are both corresponding to your data points if you've got n data points, but the dimension of them is 2. So now what we say, instead of, I'll not open this. So instead of xi transpose xj, which is written here, xi transpose xj, I would use the kernel function xi comma xj as 1 plus xi transpose xj square. So instead of having this as your kernel function here, let me change it to this. Just bear with me, let's see what happens. That's why I'm not showing you the slide. So we'll first expand this. We'll expand this. What is the square? This will be 1 plus xi transpose xj. We'll write this in an expanded form. So if we look, let's not go far away. Let's not do it in a hurry, confuse you. So let's say these were my two xi xj. And when I was writing this as a kernel function, I was xi transpose xj was xi1, xi2 times xj1 and xj2. I and j both are going from 1 to n. So that remains in this. I'm just working out inside the summation. So this will be xi1, xj1 plus xi2 and xj2. Correct? Now we say we're going to replace this guy with a different kernel function, which we call it as xi xj is equal to 1 plus xi transpose xj square. We are doing something more. Why this kernel function has come, I'll tell you later. But once we expand this, this will be 1 plus. So what is xi transpose xj? It is this thing. So I'll write this down. So it is xi1 xj1 plus xi2 xj2 whole square. Correct? Now I'll write it, expand it further. So this is 1 plus, So it will be this square plus twice of this, and then inside of this will be twice of this. So it will be 1 plus xi1 square xj1 square plus xi2 square xj2 square plus twice of this and twice of xi1 xj1 plus twice of xi2 xj2 plus a product of this. So it will be twice of xi1 xj1 xi2 xj2. Correct? This is. Now my question for you is, I want to write this as an inner product of two other functions. Remember, it has to be written as an inner product. So I want to find this phi so that this could be written. I want to write this as phi of xi transpose times phi of xj transpose. So what is this phi now? I have to, the theory says I have to replace the inner product xi transpose xj with an inner product phi I xi transpose xj, where phi is of a higher dimension than x. Can somebody tell me what this phi would be? Oh, I didn't bring chocolate. Good. Yeah. It wakes them up. Hey, you bring it every time. Huh? See if you can get silk. Okay. Question answer. I want to write this big term which I got as an inner product of two phis. So what will that phi be? Can somebody tell me? So let's try to write it down. So what if I write this as 1 xi1 xi2 square root of xi1 square root of 2xi2 square root of 2xi x1 xi1 xi2. If I write this as one vector, what will be my vertical vector to multiply with this? It will be just j, right? So 1 into 1 will give me the first term. I'll get x, so this will be xi square xi2 square. So xj1 square xj2 square then the next term is 2xi1 xj1, so it will be square root of 2 xj1 because this term will come, then square root of 2 xj2, then square root of 2 xj1 xj2. Now look at this. If I multiply this horizontal vector with this vertical vector, won't I get this? Correct? So what is my phi? Phi is my this, where it is just I is replaced with j. It's just the same. It is taking the square of the first component, the square of the second component, the first component with the square root 2, the second component with the square root 2, and then the product of the first two components, the two components multiplied by square root 2. It is I, and j. Everybody with me? So now what happened? What was your space earlier? What was the dimension of your space? 2 dimension input space. You were multiplying xi1 with xj1, xi2 with xj2. Now what is the space of your 6 dimensions. You have taken variants of the components. You have not just taken xi1 and xi2. You have taken xi1 square, xi2 square, xi1, xi2, and the product of xi, x12 and a constant. So this is what is meant by the feature space. So you have taken the input space, which is x1, x2, two-dimensional, and transformed it into, by using those two input space only. There is no other information coming. xi1 is there, xi2, and you're taking variants of those. You're computing a combination of all those and getting a feature space which is larger dimension. So the idea again is that now you have made this to be a higher dimensional space, it may become linearly separable. So the choice of the kernel function is a hyperparameter, you can say, which is something which you don't know. You have to play around, or your domain person will say, maybe, what kind of a kernel function have we used here? We have used a quadratic kernel function. We have just had the input space, we added a 1 to it for the sake of ease. You can, not do the 1 also, but we have squared it. So we made a quadratic. You can make it cubic, you can make it quartic, you can make it highly non-linear, you can make it Gaussian. So there are many variants of it, how you can increase the non-linearity of your feature space or the dimension of the feature space, and it may work. Is everybody okay? All right. This was what you were playing, those who were there in the lab that day. I was asking you, the second problem was this kernel trick. Change the kernel function and see what that happens to the data points. Everybody comfortable? Okay. So this is what I just talked is worked out here. So this is what the phi is. So these are some of the most common kernel functions. So this is a polynomial degree kernel function. Like I said, we used a quadratic. You can use a cubic, quartic, whatever you feel fits better to your problem. One which works surprisingly really well in real life is radial basis function. This is the first go-to kernel function when you have no idea. And in many of the cases still now this works really well. I have seen it. So I don't know why this works, but there is some theory about kernels which I have already uploaded on the drive, which you can read. This is beyond the scope of the class for your own understanding what are the intuitions more to choose a kernel function. And then there is the sigmoid function. So those are the most common ones. I show you what I have uploaded on the drive. So there's a lot of material on drive which so this is something about the kernels, the properties of kernels. So you can, those who have, the math person who's here, he may be able to read it more than you guys, because there's a little bit of functional analysis involved in it. You can see there's Hilbert spaces. So there is a good amount of theory going behind how you define the kernel functions. If you're interested, you can read more about this. Okay, going back to our slides. Okay, going back to our slides, we had reached here. Okay, so now strength and weaknesses of a support vector machine. The rest of the class we'll do 3 problems. So that's why I'm trying to finish this. The first is SVM, the optimization problem, was a convex problem. Everybody remembers, right? The objective function was convex because the Hessian was identity, and then the constraints were linear, which are both convex and concave. So it's a convex program. So whatever minima it will find by whatever method, it will be a global minima, not like in regression or in neural network where you have to worry about whether it's a global or not. So weaknesses, need to choose a good kernel function. So this will come with practice. The more you do, the more you will do. This is something which I wrote. Typically, the optimization problem is a quadratic optimization problem, and if you're not a CS major, you may, like electrical engineer, will just call Simplex, which is a popular solver they use. But for the sake of this class, I am making you solve. We solved the primal problem once with the cases. We'll solve the dual problem also, you'll see today, by hand. But there is a code to solve a quadratic program, which we briefly talked about the end of the optimization course, those who were there, but we didn't develop the solvers around it. But there are solvers which you would call. Now what you know is that there is a solver for solving a quadratic program which a support vector machine calls, and this is how it solves is behind the scenes. Something like this. So this is what you are aware of. Okay? So these are some software. See, these are some links. If you want to read more, I think this is, if you want to get more comfortable with kernel functions, I would say read this. Because the reason we've spent 2 lectures forming the dual problem and the soft margin is to come to this guy, the kernel. And now it is the kernel which will take it from here. Okay. Alright, so do this problem. Then this is very trivial problem. Then we'll go to the more serious problem. So this says given a data points, these are the data points which are given. You have to find the ideal hyperplane in form of if the linear SVM is of this form. So your hyperplane is of the type W transpose X plus B, or if you want to in a 2-dimensional case, it will be W1, W2 in X1, X2 plus B equal to 0, or W1, X1 plus W2, X2 plus B is equal to 0. So here it is written, this W is replaced as W naught. So that's the only difference which is done here. So what will be your ideal hyperplane for this? Correct. Everybody agrees? So if you have to write it in, what will be the value of W naught, W1 and W2? W naught is equal to -3, W1 is equal to 1, and W2 is equal to 0. Once you substitute it, you will get as X1 is equal to 3, which is your hyperplane. Just a trivial problem, just to get you started. Hai na? Just hold on. Hello? Hello? We can take this call at 10 in the class. सिग्नल यहाँ नहीं आएंगे, बाहर जाना पड़ेगा, नहीं तो मिला लेना इसी को लास्ट डायल कॉल को. Everybody okay? Yes? So now what we do, this is what is there in the slides. Now what I have done is I have added as a homework problem, but we'll do it today. So this finishes lecture 9, this finishes support vector machine. We go to interaction. Now your practice. Okay. So the practice will happen. The very first thing which we are going to do is we go to interaction. I already told you. बता दिया? Yes. Okay. Interaction तो I already told कि lecture is done. We are changing the schedule this week a little bit. Tomorrow we will have the tutorial lab here itself in the class time. And Thursday instead of the lab I will take 2 lectures. Because I have to start distance based, because we have 2 hours, 4:30 to 6:30. I'll let you know the classroom. I don't know whether this is free or not. So tomorrow, the reason is I don't want to start distance based models unless you get fully conversant with SVM. So I want you to do the problems first, then I start distance based model, and then since they are 2 hours on Friday, we'll do 2 lectures and a distance based. So for tomorrow's tutorial, there are these 4 problems which you will get more comfortable as after today's discussion. So these are problems, 2 problems on solving the dual problem, 1 problem to play around with the kernel trick. So that is what it is, which the TAs will do tomorrow. I am trusting that they will do it well. Usually I come on all of them. Tomorrow I am not coming for this because I have to travel most probably. If I am not, I'll come. So that's one thing. Silk nahi hai, dairy milk is expensive than Kit Kat. So you get a bitter chocolate now. I've got 5, so you have to ask me 5 questions at least today. Hey, one for you. You can take it. He asked a question. Come. Alright, so that is one thing. Tutorial lab, you'll do 4 problems. Now we go to offline, supporting material. I've already given you kernel PDF. We go back up for the practice. I've already uploaded more practice problems. So there are, I think, 4 practice problems or 3 practice problems. These are coming more from real life. You want the 2 feedbacks which you gave me was more problems, real life, more problems, real life. So this is real life problem, or the real life is more coming from your survey paper, but this is also real life data. Again, a kernel related problem. So there are 4 problems here, so you can practice. So now coming to what we are going today. So we are doing homework. So we're doing 2 problems in the homework. There are 4 problems for tomorrow tutorial lab. There are 4 problems for practice. So total there are 10, and including 1 problem in the lecture, there are 11 problems you're doing, and 1 problem we already did earlier. So you've done 12 problems on SVM. You have to get comfortable covering whole spectrum, solving the primal problem, conversant with the dual problem with the soft margin and the kernel. Everybody okay in terms of what will make you comfortable in practicing? Yes, this side I don't see much, but yeah. Okay, so now let's do 2 problems which I have made as homework. We'll see how far we can finish, but we'll try. Hannah, you do with me. Okay, so the first problem goes like this. So you've given this and this will answer some of the open-ended questions which are still remaining. How do you find the support vectors? Because you're using all data points to build your SVM, if you have to figure out which of them are support vectors, how to figure it out. So that also we'll answer it today. So you're given this data points 1, 2, -1, 2, -1 and -1. So if you have to, so this is homework 3 question. So if you have to draw this, so the first point is x is 1, y is 2. The second is x is -1 and y is 2. The third point is x is -1 and y is -2. So this is belonging to a different class, and these 2 are belonging to a different class. So that is what is given to you. You have to do is convert, well, first write the dual form. Do it without the soft margin. So we're doing this problem, plain vanilla dual problem. So let's first write it down. So everybody agrees this is the dual problem. Now you should remember it. Nothing. This is summation alpha j y j x I transpose plus alpha I, and this summation and alpha greater than 0. If there was a soft margin, then you would be given a C, which you would play around as a hyperparameter, and that will be bounded. This is a bound up above. That will be a lower bound to the alpha. Okay? So that is given to you. Now, how do you solve it? There are 2 ways of solving it. What did I tell you? Now, going back all the way to optimization. Yeah. So there is this cases. Let's just recall. Where we talked about the primal problem, right? So this is what we did. What do we do? This was for the primal problem, right? This was our primal problem, and then we had written the KKT conditions. Once we had written the KKT conditions, then we had applied the cases and then solved it, correct? Because there was this alphas which you're doing. But there's an easier way of doing it, which is converting the constrained problem to an unconstrained problem and just applying the necessary and sufficient condition for an unconstrained problem. What is a necessary condition for an unconstrained problem? Gradient is equal to 0. Gradient is 0, which in this case, everything, no necessary was needed, so that will become your sufficiency condition, global minima. So just have to make gradient equal to 0. So the first homework problem, we are going to just find the gradient of the Lagrangian and convert the problem to an unconstrained and then make the gradient equal to 0. Is that okay? So that is what is done in the first homework problem. So we go back to offline. homework, first problem, constrained and unconstrained. So that's why it's written, find using the method known as conversion of constrained to unconstrained. Okay. So what we do, we take the data points and we fill this up. You can see it becomes really hairy. Solve it a little bit, but now we had two constraints. We had this linear constraint and then we had the non-negativity constraint. So we'll take the linear constraint and substitute it in our objective function, which is the Lagrangian here. So we are taking this summation. We are putting this equal to 0. So alpha 3 is alpha 1, alpha 2. We are going to take this and substitute in this hairy expression. So there is a tendency to do mistake here, by the way. When I take exams, I usually don't worry about errors happening because of computation. But if errors happen too early, then you get a completely wrong answer. If they happen later, you get a lesser answer. But doesn't mean that if you're not exactly matching the answer, I'll give you 0. You'll see after I grade the quiz, we'll get more idea about how I grade. I'm a lenient grader. I do want to see an attempt that you have taken an effort to do it. So that is more important. Okay. So you take that, you substitute it, and then once you substitute it, you get this as your function. And then what we do is we take partials, so what we do is, for the moment, we ignore the non-negativity on alpha. I mean, there's a non-negativity on alpha also, which you can not ignore, but you can write alpha as gamma square. Okay, we're doing it too fast, I'll tell you. Hold on. Everybody comfortable with the dual problem first? I'm going to go over again. This is a standard form without soft margin. What I did, there were 3 points, x1, x2, x3 and y1, y2, y3. We substituted it and we got this hairy Lagrangian function. Everybody agrees? But there are two constraints to it. A linear constraint and a non-negativity constraint. Is that okay? So what we'll do, we'll eliminate both the constraints and make it into an unconstrained problem. The advantage of making it an unconstrained problem is, you have to only work with you only have to come and work with only the gradient equal to 0. You don't have to apply the 5 KKT condition. The equality, the inequality, the Lagrange multiplier, the complementarity, the non-negativity, you don't have to worry about the 5. So if you can easily transform a constraint to an unconstrained, then you make your life easier. So that is what we are doing now. Once we get this hairy expression, we look at the first constraint. The first constraint is this. I write it down. I get alpha 3 is alpha 1 plus alpha 2. I'll take it and substitute in the hairy expression. Everybody with me? I'll make you work this out in the next problem, so you will be able to get more comfort. So once you do that, put equation 2 in equation 1, you will end up with this. Now you can look at this, doesn't look too hairy. Correct? Everybody can see? It looks simpler. But there was another constraint. What was the another constraint? The non-negativity constraint. Alpha is greater than 0. So those who did optimization, because I think in the 2 optimization extra lectures I probably didn't cover this, that whenever you have a function, let's say alpha 1 greater than equal to 0, you can write alpha 1 as gamma 1 square. You can do a substitution. What that brings you in? Gamma 1 square is anyways greater than equal to 0, so there is no constraint on the problem. Can you see it? Everybody okay? Yes or no? Okay. So now we go further down and we do this. We substitute alpha 1 as gamma square and alpha 2 as gamma square, and we end up with this equation. So what we did, we took the original Lagrangian, put the data points, took the 2 constraints, substituted them back into the function, and now we're only left with the function, no constraint. So now what makes our life easier? Just make gradient equal to 0. Whatever point you will get will be a global minimizer. Everybody with me? Okay. So we differentiate with respect to gamma 1, gamma 2, and we solve it. So we get gamma 1 square 0, gamma 2 square this, gamma 3 square this. And then we get that alpha 1 is 0 and alpha 2 and alpha 3 both are 1/8. ठीक है, इसको घर जाके कर लेना. If this is becoming faster, once you work it out yourself, it becomes easier. Okay? Alright. So now what do? What did we have to find? We had to find W, we had to find the margin, we had to find the B, we had to find the support vectors. Those are the 4 things we had to find. Now what was W? How was W defined? कुलदीप ये एक बार देख लेना, घर से आ रहा है कॉल. Can you tell her that I'm still in class? Tell her that auto wala has said no, है ना? It was something. So where was I? So we have to find W. So now how was W defined? Let's go back before I show you where this was, so that you can recall it better. When we were doing the lectures and we wrote the example, we had written that, sorry, in the introduction itself, in the formulation, at the very last slide, यहाँ कहीं खो गया है, कहीं कहाँ था, डुअल प्रॉब्लम में था. This is where we had written, because we had substituted this, na? W bar was alpha I, yi, xi. So we're going to just substitute that. Okay. So we're going to go back to our homework. So we had defined that W will be alpha I, xi, yi. So we substituted it. Alpha 1 is 0, alpha 2 is 1/8, alpha 3 is 1/8, y1 is, we don't need, y2 is -1, y3 is 1. x2 is this and x3 is this, and you get W as this. Okay? Now how was the margin defined? 2 over norm of W. So 2 over norm of W is 4. So straightforwardly done. Now B, how can B obtained? B can be obtained from any of the points. We know that y transpose W transpose x plus B is equal to 1, for the points which, for the support vectors. Okay. Now how do we define a support vector first? So support vector is defined corresponding to the alpha values which are not equal to 0. Why is that? Again, we'll go back. So we go back to interaction, lectures, and okay. So going back to the primal problem, you can argue this with the dual problem as well. I'm just telling you with the primal problem. This was the primal problem, everybody agrees. When we wrote its Lagrangian, what did we do? We took Lagrange multiplier and the constraint and subtracted it from the objective function. Alpha 1 minus the first constraint, alpha 2 minus the second constraint, alpha 3 minus the third constraint. Now if one of the alphas is becoming equal to 0, which means that that constraint is no longer playing a role. Everybody agrees? Constraints are coming from the boundaries. If the point is not playing a role, which means that it is not on the boundary, it is somewhere away from the boundary. So hence, where alpha is equal to 0, those are not your support vectors. Where alpha is non-negative, they become your support vectors. Can everybody see it? Yes or no? Okay. So that is what we do. Go back again. So this is what we'll answer the D part. Since alpha 1 is 0, x1 is not a support vector, x2 and x3 are the support vectors. Now what are the support vectors? They are at the boundary. Correct? Remember? This was W transpose X plus B is equal to 0, W transpose X plus B is equal to plus 1, W transpose X plus B is equal to minus 1. It doesn't matter where plus 1 or minus 1 you take. Eventually the constraint which we had written at was Y1 W transpose Xi plus B greater than equal to 1 when we were doing it for both of them. Correct? One is a plus 1. So which means that if you are at this boundary or you are at this boundary, this will not be greater than equal to 1, this will be equal to 1. Correct? So for any of the support vectors, you use that and substitute to get your B. So for without loss of generality, I do it for x2. So I do y2 w2 x2 plus b is equal to 1, y2 is minus 1, w2 is 0 and minus half, which we just found out. It comes out to be minus half, I think. There's a typo here, है ना? Fix this. This should be minus half. Should be, it will be 0, 1 over minus. कुछ गलत हो रहा है यहाँ पे. It should be minus 1 by 2, right? So that is what the problem is. ठीक है, तो ये minus होना चाहिए, fix it. So you put minus 1 over 2, x2 is minus 1 and 2, b is known, so then b will turn out to be 0. So which means that it is just the hyperplane 0, minus half. That is what your hyperplane is. Everybody okay? Comfortable? Okay. So now to get you that, sometimes it's good to know to apply the KKT conditions. This one is without converting the problem to an unconstrained problem. There it was easier because I only had 3, correct? And I was easily able to eliminate alpha 3 is equal to alpha 1 plus alpha 2, put the square. Imagine having 10, how much of algebra will you work out? I mean, of course, the program will do this for you, the quadratic program which you will solve, which we have not told you, which covered in the optimization course, but underline it will do something. So it will probably apply the KKT condition. So now the same problem, the data points are the same. If we have to do the KKT conditions, okay, we have time. So we wrote it as a dual problem, correct? We wrote the objective function, but now what we'll do is we'll write the KKT conditions. Okay, so what are the KKT conditions? Can somebody come with me and guide me? First is equality constraint, correct? Second is the inequality, which is the third is the Lagrange multiplier, correct? So now we have, this is the objective function and this is your Lagrange. This should be lambda I, by the way. I don't know why the lambda should be inside. There's a mistake here. Why is it written lambda inside? No, this is only one constraint, na? So it will be just lambda. This is only one constraint, alpha 1 y1 plus alpha 2 y2 plus alpha 3 y3. There's only one constraint. If there were multiple constraints, then we had multiple lambdas. But we have multiple inequality constraints, alpha 1 greater than 0, alpha 2 till alpha n greater than 0, alpha 3. So we have 3 mu's, mu1, mu2, mu3. So now you can see the difference why we were using alphas and not using lambda and mu, because lambda and mu come in while solving the dual problem. So that's why we used alpha earlier. So this is second. The third one is the two multiplication lambda times the constraint equal to 0, although this one is not needed because this is already equal to 0, we told already. And the other one is the complementarity between mu I alpha and non-negativity on mu. Now how will you solve it? So we'll do the cases. So one constraint is active, second and inactive. So you'll solve from this. Then the third constraint, so you'll get the same answer. Everybody okay? Okay. So what was it? So you can go over this, है ना? I think that's what I wanted to cover. We'll probably finish early. It's 25. If you have any questions, then you can ask me, or we can briefly go over the problems which you're going to work on, है ना? So those are the two problems. We'll first go over the tutorial problems, then we'll go over the practice problem, है ना? Which you will do. Okay. So you can see this is the first problem which you will do. इसमें लिखा हुआ है apply KKT condition and find the minimizer. So this is simple. You will apply the cases and do it. This is where you are playing with the kernel. So here you have a different kind of a kernel function given, and now you have to play around and see what happens, which one will work and which one will not work, है ना? This is showing you why the choice of this kernel function makes your data linearly separable, which is the reason that we are making it to a higher dimensional space. Can everybody see this? You will do it tomorrow, है ना? Then it will be more clear. Then this is another problem which is standard in kernel. It's called the XOR problem. Those who are from electrical engineering may be comfortable. CS also may have done XOR problem somewhere. If you have not done, it's nothing foreign. XOR is a function which decides where, when, what values come. Here we say that when you take a quadratic polynomial kernel for the XOR problem, it becomes linearly separable. So I'm showing you another example where earlier it was not linearly separable. So in this question 3 of tutorial 5, the data points were something like this. They were, one point was here, here and here and here, something like this. So the data was not linearly separable. When you able to transform it, it became linearly separable. So this is what it is talking about, the kernel. You work it out, taking to a higher dimensional space. You can see it's slightly hairy. So now it becomes linearly separable, the points. Okay, this only 3 problems are there for tomorrow, but they are important. So make sure you work it out. But the homework also, let me just go over, because then Thursday I'll not talk about anything about SVM unless you ask me any questions. So not homework, the practice problems. So offline, practice, SVM. So this is real world, this is more of analytical problem. Look, this is with the soft margin. Because we have not played around with the soft margin, this problem helps you get more comfortable with it. What values of zeta you should pick and which one you should not pick. This is again soft and hard margin with a different kernel function. This is again with the penalty parameter, so soft margin, justify why this is used. This is again with kernel, because you guys have not done much of kernel functions, so again something on kernel functions, and that's it. So I think with all these problems, for the first problem on primal with the codes we did cases, one problem with the codes we did at the end of the lectures today, 5th, one in lecture 2, lecture 5th. We did 2 problems today, 4, 3 problems in tutorial tomorrow, and 4 problems in homework. So by end of it, you should be happy with SVM, I feel. If not, then ask me. But then real life, your papers. So since we are not meeting this, so on Thursday, you can tell me if you have zeroed down on your papers, although I plan to take 2 lectures. If you want, I can take 1 lecture and do 1 lecture discussion of the survey paper. Is that better for you, or what would you prefer? Any preference? No preference? We'll see how it goes. You do the tutorial tomorrow, 1 lecture on distance-based model. The second lecture we'll see if you're comfortable, we'll do, otherwise we'll discuss your survey paper. So bring your laptops. The room I'll tell you over email, because I don't know whether this room is free Thursday 4:30 to 6:30. You'll not go to the lab. ठीक है? Sorry? Yeah. Sorry? कल नहीं, परसों. कल तो हाथ से वर्कआउट करना है ना. These are all analytical problems. Thursday, bring your laptops, whether we do it in this room or we do it in the Gargi. I'll check whichever is free. I mean, anyways, you not more than 40-50 students come, so we can do it in a normal classroom also. We don't have to take a big classroom. I'll let you know. Okay? Okay. In terms of the quiz, I may have to change the quiz. I may take it on Wednesday instead of Monday. I'm not sure because I may travel on Wednesday, so that's why I'm thinking. I'll let you know on Thursday. Okay. Thank you. देखो क्वेश्चन नहीं पूछा ना 3 चॉकलेट